calculating areas using upper and lower rectangles. I guess this should be approximating areas using upper and lower rectangles. Suppose you have the function f of x equal x squared, and you want to approximate the area from 1 to 5 using n equals 4 rectangles. N is the number of rectangles. Well, let's see what's going on. Oh, and we're going to use, first, we're going to use upper rectangles. So here is the function y equals, or f of x equal x squared, and as stated, we want to go from 1 to 5. And we're going to make 4 rectangles. That's going to be 1. I just need to draw the top clearly. That's going to be the second, the third, and the fourth. So here is going to be our 5. And actually, let us first do lower rectangles. Let us find a lower estimate. So let's number these. That's going to be 2, 3, 4, and 5. Nice numbers. Now, between 1 and 2, between f of 1 and f of 2, f of 1 is lower. So that's my first rectangle. Between x equaling 2 and x equaling 3, between those heights, it turns out that the one I just picked is the lower one. And then between 3 and 4, it happens to be that 3 is lower. It doesn't always have to be the left end point. And then, so that's the second rectangle, the third. And then between 4 and 5, between f of 4 and f of 5, f of 4 was the lower one. So there's our 4 rectangles. Now, what is the area of those 4 rectangles? Well, let us concentrate, zoom in on the first rectangle. Well, the base is 1, so it's 1 times the height. Well, the height is that height. The height is f of 1, which is 1 squared, which itself is 1, plus the second rectangle, so I'll say s, little s, small s for lower. Now we talk about the second rectangle. The base is still 1. And the height is here. It's that height, but I don't really know what that height is, but I can figure out what that height is. That height is f of 2, which is 4. And then we go to the third rectangle, which will be this rectangle right here. And once again, the base is 1, and the height is this amount. Oh, that's f of 3, which is 3 squared. And then the last rectangle over here, the base is 1, and the height is f of 4, which is 16. So we get 1 plus 4 plus 9 plus 16. In fact, we can factor out the base. So it's the base times 9 and 16 is 25, 29, 30. Okay, so we claim that little s is 30. Now we want to find out what big S is. Big S is going to be the upper rectangles, excuse me. So we have the same exact graph, and we're still going from 1 to 5, 2, 3, 4, and 5. 2, 3, 4, and 5. Now this time, between 1 and 2, we pick the larger height. That is, that's going to be the first rectangle. The second rectangle, between 2 and 3, the height is larger at 3. So this is going to be the second rectangle. And the third rectangle is going to be between those, we're going to pick between those two heights, and the one to the right happen to be larger. So that's going to be the third rectangle. 1, 2, 3, and then the last rectangle goes between x equals 4 and x equals 5, and it turns out that the higher height is at 5. So big S, well, all the bases happen to be the same. They're 1. So let's just multiply by the heights. The height of the first rectangle is f of 2. 2 squared is 4. The second rectangle, the height is f of 3, which is 9. In the third rectangle, the height is up here, which is f of 4, which is 4 squared. And lastly, the fourth rectangle, the height is up here. I mean, it's also up here, but that point is not on the curve y equals x squared. This point is. Oh, that point is f of whatever number I see here. And that happens to be 5. So it is 5 squared. 25. Another 25 is 50. Plus 4 is 54. Times 1 is 54. So that's the upper estimate. The upper estimate is 54. Now, let us talk about why the first one is a little bit off. Why it's lower. And I think it's obvious. We didn't count this area. We didn't count this area. We didn't count that area. And we didn't count this area. And we were supposed to. Okay, that's why it's lower. Why is the other one higher? Well, it's kind of clear. We added this area. We added this area here, this area in here, when we weren't supposed to. We only want what's below the curve. We only want what's below the curve. We only want that area. So we added in too much. We added in too much. That's why it's above. Now, what would happen if we put in more rectangles? Of course, between 1 and 5. 1, 2, 3, 4, and 5. Well, for example, if we just put in one rectangle and we compute the lower one, well then, that would be the one rectangle. We would get this area, and we would miss all of this area. Well, what would happen if we put in a second rectangle? Well, that means that the base, which is b minus a over the number of intervals, this would tell me that b is 5, a is 1, and we're going to do 2 intervals. So it's 4 over 2, which is 2. That is, here's 1, I go 2 over, and then 2 over. Here would be my second one. Now, if we're doing the lower triangular one, well, the first rectangle gave us this area when we only had one rectangle. Now that we have 2 rectangles, I still get this area, but now I get this area. That is, we're now counting this. We weren't before. Well, that's good. What if I let n be 4? That is, oh, don't ask me why I have a 2 here. Now, if I cut it in half again, well, for the first rectangle, nothing new happens. Between these 2 heights, I pick the lower one, and I still get this. But now, between x equals 2 and x equals 3, I'm going to pick 2, because 2's lower. And then I get all of this area. That is, I suddenly now am counting this. And between 3 and 4, well, nothing's going to change between 3 and 4. I pick the lower rectangle, the lower height, and I still have this. But now, from 4 to 5, I pick between these 2 heights, I pick this height, and now I have this rectangle. So now I'm adding all of this. That is, I'm adding this extra. I added a lot more. My error is the black space there and here and here and here. If I partition it in half again, if I put it in half again, so now it's 1.5, 2.5, 3.5, and 4.5. Well, now I am going to add in this area here. Between 2.5 and 3, I take the lower height. So I'm going to add in this piece here, and that little spot there that's barely black will stay black. At 3.5, I'm now going to add in this area, which wasn't before. And at 4.5, I'm going to add in this area. So my error is less. My error is this piece here, this little piece there, that little piece there, this piece, this piece, this piece, and this piece. Now, it's hard to see what's going on for small x values because the errors are really small. But let's look at between 4 and 5. If I also put another line between 4 and 4.5, and I put another line between 4.5 and 5, and then between these 2 endpoints, I pick the lower one. Well, now I am filling that in. And between 4.5, between 4.5 and this new mark, I guess, which is 4.75. I meant to say between 4.75 and 5. Between those, I take the lower endpoint, and then I fill in this big rectangle. That is, I now fill this in. Okay, so each time I partition, like between 3.25 and 3.5, between this height and this height, well, right now I have this blank. I'm not counting that. But now I'm counting that as well as this. That is, my only error is there. My error used to be all of that. Everything in the green. Now, it's only that small looking triangular region. The bigger that n gets, the more of these errors we fill in. The more we fill in. And if you see where this is going, if I let the number of rectangles go to infinity, it's gonna fill it all in. Likewise, when it came to using the upper triangular regions, if between 1 and 2, I put another 1. Okay, so now I've been counting everything in here. That's an overestimate. I've been also counting this. So I'm counting all of this when I just went from 1 to 2. So I have overestimate of what's in blue. That's the overestimate. Okay, so now that I suddenly put in this new line, this new partition at 1.5, well, now when it goes between 1 and 1.5, between this height and this height, I'm picking the larger one, which is here. That is, this area up here, I am no longer counting. Okay, I am no longer counting that. Now between 2 and 3, it looks a lot bigger, it looks a little bigger than the others, so let's use that. What's in solid pink up there is my overestimate. Now, if I draw in the line 2.5, I admit that between 2 and 2.5, between 2 and 2.5, between 2 and 2.5, I'm only going to count that amount. That is, this in here, I'm no longer counting. So my error, my overestimate got smaller. Now, between 2.5 and 3, I'm still going to count my overestimate. It's still going to count this overestimate. But in the left where I have the dots, I'm not counting it anymore. The more partition that I put in, the overestimate gets smaller and smaller and smaller. For example, when I put in 2.5, I'm no longer counting that overestimate. So my overestimate is now this. I got rid of all of that overestimate. And as n goes to infinity, this overestimate is going to get smaller and smaller. Okay. Suppose we have another function, which is f of x equals to x cubed plus 1. And n equals 6. Now, and we want to do it from 1 to 3. Now, if you were to look at the interval from 1 to 3, if you're only going to have one rectangle, then the base will be b minus a, 3 minus 1 over 1, one rectangle. So you get 2 over 1, which is 2. That is, the base is 2. Now, if you put 2 rectangles, then delta x, the length of a base, will be 3 minus 1, which is still 2. And now we're dividing it by 2, which is 1, which makes sense. This will be 1 unit, and this will be another unit length. But what if I divide it into 3 pieces? 3 minus 1 is still 2, but I'm going to divide that length of 2 by 3. I'm going to divide it by 3. 1, 2, 3. I now have 3 intervals. And I claim that each width, each base, is 2/3. Well, I mean, it makes sense. The whole distance is 2, and I partitioned it into 3 regions. So this will be 1 2/3, because 1 plus 2/3 is 1 2/3, and 1 2/3 plus another 1 will be 1 4/3, but this is 1 plus 4/3, and 4/3 is 1 1/3. So 1 1/3. So I get 2 1/3. This mark is 2 1/3. This working like a charm, because if I add 2/3, then I get 2 3/3, which is 3, the end point. And one last time, if I divide the base into 4 equal intervals to get 4 rectangles, divided into 4 equal pieces, and this is 1 3, well then delta x is just going to be 2 divided by 4. Dividing it into 4 intervals. So you get 2 over 4, which is a half. 1, that's 1. This is going to be 1 1/2, that's 2, and this is 2 1/2, and our check is, yep, that's 3. So it makes sense that delta x is the right formula. That is, it's the right endpoint, which is 3, minus the left endpoint over the number n. Okay. So we're told in this case that n is equal to 6. So delta x, the base, is going to be b minus a, 3 minus 1 over 6, which is 2 over 6, which is a third. So when it comes to the base, this is going to be 1, and then 1 1/3, and a third, and then 1 2/3, and then 2, and then 2 1/3, and then 2 2/3, and then 3, from 1 to 3. And the graph, it's a cubic, it looks something like this, just up, up, and away. So now, if we have our 6 intervals, and we're going to say pick the lower one, it'll be this one, and then this one, and between these two, it'll be this one, the lower of the two. Not necessarily the left one. Between those two there. So these are our 6 rectangles. And each base is 1/3. So little s, because we're doing the lower sum, is going to be the base times all the heights. Well, this height for this rectangle, it's on the curve right here. Okay, so it's going to be f of 1. So it's 1 cubed plus 1. 1 cubed is 1 plus 1. So let me just write it as 1 cubed plus 1. Plus we'll think of that as 4/3, and this is 5/3, and this is 7/3 and 8/3. Okay, so for the next rectangle, for this one, between these endpoints, only this one's on the curve. Between these two endpoints, okay, between this endpoint and this endpoint, that one's lower. That's why we make this rectangle, and it's going to be f of 2, which is 2 cubed plus 1. 4/3 squared plus 1. It's going to be f of, not the rectangle number, I apologize, but f of 4/3. So it'll be 4/3 cubed plus 1. For the third rectangle, between this height here, and that height, this one's lower. And that's the point on the curve. Okay, nowhere along here do I hit the curve except right there. So it's going to be f for 5/3. 5/3 cubed plus 1. And then that's for first, second, the third. For the fourth rectangle, between this point and this point, this one's lower. And f of 2 is on the curve. So it's going to be 2 cubed plus 1. And then for the fifth rectangle, between those two heights, that's the lower one, which is 7/3. So it's going to be 7/3 cubed plus 1. That's for the fifth rectangle. And for that last rectangle, it's going to be this height here, which is f of 8/3. So it's going to be 8/3 cubed plus 1. And we don't need these numbers here. And you can calculate this. I'm not. Okay, that is, you can cube 4/3 and then add 1 to it. You can cube 5/3 and add 1. And 2 cubed plus 1, that's easy enough. It's 9. You can calculate this and this, and you can get all the denominators to be 27. And you work it out. And when it comes to the big S, and since this function is increasing, we're not going to get the first one, because between these two heights, we're going to use the higher one. But this area is the same as what area 2 was. So it's really going to be all of this plus the last one. It's going to be 4/3 cubed plus 1, 5/3 cubed plus 1, 6/3 cubed plus 1, which is 2 cubed plus 1. It's going to be 7/3 cubed plus 1 plus 1. It's going to be 8/3 cubed plus 1. And then the last one, between these two endpoints, that's the larger one. So we're going to use this rectangle. Well, that's f of 3. That's going to be 3 cubed plus 1. So we can go from one to the other somewhat quickly. We don't count the first one, and we add the last one. And then for little s, we do count the first one, but we don't add on this last one. Okay. This is only because the function is increasing. We know that x cubed goes like that, so x cubed plus 1 will go like that. So in particular, when x is between 1 and 3, this function is strictly increasing. So when it comes to picking the lower one, between 1 and that value, it's always going to be the left endpoint. Between those two x values, it's going to be the left endpoint. And when it comes to the last one, it's also going to be the lower one. But now, when we do the same game and we want the upper one, however many partitions we put, doesn't matter. When it comes to the endpoints between 1 and the first partition, we are not going to pick this endpoint. We're going to pick the right one. But that's exactly what we picked for the second one. And now, for the next to the last, we're going to pick this one. But that's basically what we picked for the last one. We just went that way. This area and this area are the same. The thing is that for the last one, we're going to pick the higher one. We're going to pick this one, which we didn't pick here. We never included this one. We did include the first, but here we didn't include the first. That is, we never included something with that height. We didn't include it. So it's the first and last that changes. That's only if the function is strictly increasing or strictly decreasing. That finishes this section on approximating areas using upper and lower rectangles.